Okay, thanks, Carol. I'm going to be talking today about a technology issue in the history of skyscrapers. History of skyscrapers is a very big topic. And when you look at the buildings, sometimes it can be hard to sort of distinguish what's going on in the early days. When you look at a tall building from 1880 or 1890 or 1900, they all sort of look the same. And there are big changes happening hidden inside in the building frame technology. And those changes affect both the buildings that could be built. So buildings are getting taller because they're using the new technology. But also the way designers and contractors thought about the buildings. So it's worth looking at these sort of obscure changes, A, for the technology and what it represents, and B, people need a reason to change what they're doing. And getting better safety is a good reason. If you can speed up construction, that's a good reason. But one of the overriding reasons is cost. And there's a change in the cost as you change the technology. So I want to just discuss that a little bit for the same details I'm talking about. This is an illustration from the front page of Scientific American in 1888. It is showing, it is showing the old New York Times building being swallowed up by the new New York Times building, which was built around it and over it. The picture on the upper left shows the building as it was completed and as it stands today. And the important thing about this picture is it shows construction happening the way it always had happened. People are lifting up stones and putting them on top of stones, building these walls from the bottom up. The interior floor framing was connected to those walls. The structure that holds up the floors was connected to the walls, so it couldn't get very much beyond the top of the walls. If the top of the walls are 2.5 stories above ground, the floor is 1 story above that. And that's about as far as you could go safely. You couldn't build the whole 10 or 12 stories of building with the walls only 2.5 stories up. It would collapse. So this is construction as it had been forever. And when I say here that the pace of the floor construction was determined by the pace of the wall construction, that meant that if you live in a cold climate, and New York and Chicago, the place where tall buildings develop first, both have cold winters. If you live in a cold climate, you can't build masonry during the winter. So it was a normal event for a large building like this to take 2 or 3 years to construct, because there would be 4 months where you couldn't build masonry, and therefore you couldn't build the floors. The whole process would grind to a halt. What determines the cost of a building? Any building. The Times building that I just showed, or any other building. And this is in terms of any physical part of the building. These same factors come into play. The first is the raw material. All of the examples I'm going to use here are structural examples, but this would apply to windows, this would apply to interior finishes like plaster. It applies to any piece of the building. So you have to actually make the material. And that could be a foundry casting iron. It could be cutting down trees and putting them into a lumber mill to turn them into wood joists. Anything where you're creating the raw material. The next thing you have to do, sometimes, you don't have to do this for every material, is take that raw material and use it in a way, or fabricate it in a way that is useful in the building that you're going to build. This step doesn't really apply to cast iron because you cast it in the shape that you want. It does apply to steel, and to this day, a mill will roll a steel beam, and it's 40 feet long and undifferentiated along its length. Well, if in the building you need a piece of steel that's 27 feet and 1 inch long, and it needs holes for bolts at the end, or in the 19th century rivets, maybe it needs some cuts in it, all of that fabrication has to be done after the actual material is created. Bricks don't require fabrication. Cast iron doesn't require fabrication after the original creation, but wood does, steel does, and so on. If you're talking about reinforced concrete, the buildings I'm talking about are mostly before reinforced concrete. The concrete itself doesn't require fabrication, but the rebar does. So that step is Not always there, but often there. You need to get the material to the city where you're building the building. New York City had cast iron foundries, but we didn't have steel mills. Boston didn't have anybody making Portland cement, because you need limestone to make Portland cement, and that's not what the bedrock is around Boston. So cement had to be shipped to Boston, steel had to be shipped to New York. And it could be shipped from different places, but this is a cost that comes into play. Then you have local shipping. Something comes into a railroad terminal, it has to be brought to the site. That doesn't seem like a big deal, but keep in mind this is before mechanized transportation. So if you have very heavy objects that have to be moved, it's a big deal. You get a wagon with a bunch of horses, and it can take a very long time to move the material to the construction site where you need it. And then you have actually building the thing, putting that material where it belongs in the final building. That's steel erection, that's laying brick to build a wall, that's plastering the wall on the inside, and so on and so on. It's the part that people think of as construction, and that's where a lot of the labor cost is in that. That is the part which to this day has resisted mechanization to a great extent. Whereas a lot of the other parts of this process can be mechanized, and in some cases were mechanized as far back as the 19th century. So these are the things you're looking at if you're saying, should I go with technology A or technology B? You're going to use these costs to figure out which one you should try to use. So this slide requires a bit of explanation. William Fryer was an engineer. He had some training as an architect. He had worked for the New York City Building Department. It was the Bureau of Buildings at that time. After he left the city government, he then spent the rest of his career as a consultant, basically advising architects and engineers and building owners and contractors on the new technology and how to use it. He was an expert in the technology itself. He was also an expert in the way it was regulated in New York, which gave him an edge and kept him in business. So this is from an article he wrote for the Architectural Record in 1891, and he was explaining skeleton frame technology to architects. The thing to keep in mind is that the first two skeleton frame buildings ever constructed were constructed in 1890. In 1891, there were 4 or 5 of them total. And so he's talking about this very early on in its history. One other important thing to note, particularly if you look at this drawing right here, he's talking about construction using cast iron columns. That is a cast iron column he has drawn to accompany his talk. True skeleton frame technology doesn't use cast iron columns. And I need to just talk about the types of building technology here for a minute. Up until the mid-1880s, pretty much all buildings were using bearing wall technology. You had masonry walls supporting the interior floors, like the Times building that I showed earlier. Certainly after 1900, but what developed in the long term was a skeleton frame building where the metal frame, usually steel, supports the masonry walls as well as the interior floors. In between, there was a hybrid called cage framing, where there's a frame that supports the gravity load, but it relied on the exterior masonry walls to make sure that the building didn't tip over in the wind. And the exterior walls supported their own weight. So it's sort of a hybrid. It's important to remember that at the time, people didn't think of it as a hybrid. They thought of it as an alternate to bearing wall construction, and it turned out to be a technological dead end. We're looking back on it now and we say, oh, that was a step towards skeleton framing, but that's not the way people saw it in 1885. These 3 pictures here are what's called a plan section. It's as if you cut through the column here and we're looking down. This is a column, here's a wall, here's the floor framing coming into the column. So in this axonometric drawing, what Fryer is showing is the metal frame is supporting the floors, and the cast iron columns are embedded in the mass of the masonry wall. What he's showing here, and the text that accompanies this, he's describing how you got to this place. And he said originally, you would put a cast iron column inside the building next to the masonry if the masonry pier was not sufficient to carry the load. In other words, he's talking about the engineering concept of stress in the masonry pier. Is the floor load, is the load from the floors above that's in the brick too much for the brick to carry? If it is, you remove the floor load by putting a column inside and you pick up the floor load rather than letting it go to the exterior wall. The problem with that is that you have a frame that's not really connected to the wall. Also, you have this bump on the inside of the wall, which is a problem in terms of using the space. So the next step is to push that column into the pier. That's this middle picture here. And you're still doing the same thing, but what you've now got, you've gotten rid of the bump, and you've got a little bit of interaction between the column and the pier. And then the final step is to have the column well within the masonry pier. And now the two of them are forced to act together. And that matters, again, in terms of lateral load. If the wind is blowing on the building and the walls are providing your stiffness that the building doesn't just flop over, you want that tied to the metal frame. And the easiest way to tie it to the metal frame is to embed the column inside the masonry. So when he's drawing the full thing, he's showing the column fully surrounded by masonry as a way of tying it all together. This is a cage frame building, and it was, in 1885, a fairly new idea. By 1891, when Fryer's writing this article, it was already the older technology, skeleton frame technology, had come along. In skeleton frame technology, you're going to have beams connected to the columns that carry the wall. So the wall is no longer providing you with structural stability, and it's no longer carrying its own weight. The frame is doing all of the work. That's what turned out to be the best system that was usable in the 1890s. So this is an early 1880s building, the Dakota Apartments in New York. It's a little hard to tell from this picture. It's 7 stories and another 3 stories in this incredibly complicated roof. This is the first floor plan. And what's important about this plan is all of these dark lines represent big brick walls. And when I say big, at the 7th floor, they're 2 feet thick. They're thicker at the first floor. The Dakota is still around. It's a very nice building. One of the reasons it's nice for anybody who's lived in a New York apartment is that you have at least 2 feet of brick between you and your neighbors. And that's a great thing to have. But what you don't see in this plan is columns, because there are none. All of the interior floors are carried on these brick walls. There are some columns in the courtyard where the basement or the cellar runs underneath the courtyard, and there are a few columns up in that very complicated roof. But the main body of the building has no columns. All it has is these brick walls. So this is a barren wall building. And again, this has got wrought iron beams carrying masonry floors, terracotta tile arch floors. That is relatively modern. But other than that, the concept of barren walls carrying the floors, that's as old technology as you get. That has been around thousands of years. The version of it using wrought iron beams and tile arch floors had been around by the time this was built already for about 15 years. So this is a backward-looking building structurally. This is 1885. William LeBaron Jenney designed the structure and the architecture for this building. I should point out this picture on the left here is after 2 floors were added around 1900. The building was originally 9 stories with a tall basement. The drawing on the right shows the framing layout. And here's a cast iron column, here's a girder, here's your interior floor. This looks a lot like Fryer's drawing. The rest of this shaded area here, is the exterior wall. And it is not being carried by the frame in the normal sense. Excuse me. The only continuous beam here is entirely inboard of the wall. So it's not carrying the wall. And what you've got is a combination of the piers, cast iron lintels, and cast iron mullions serving as sort of miniature columns. In the end, it's a bearing wall, but it is tied into the frame by the simple expedient of having the exterior columns embedded in those masonry piers, exactly the way Fryer was describing a few years later. This is 1885, and this is actually the first full cage frame building, the first time that the exterior wall was not supporting any of the interior floor weight. This is a few years later in Chicago, Daniel Burnham, and these two drawings show the corner of the building. This is the way the architect sees it, and we've got masonry wrapping around the corner, as you can see right here. And then here's the engineering drawing that goes with that. There's the corner column. There are the beams that support the wall. And then this stuff out here is what's called a shelf angle. And that's simply a secondary piece of steel that supports the wall off of the main beams. In other words, all of the masonry that you see in this photograph is supported on these angles, which are then hung from the spandrel beams, and the load goes back to the column. If you remove any of that masonry, the frame stands there just fine. So that is a skeleton frame building, as was constructed in 1895. So these are sort of the three stages in evolution, and they match up with what Fryer was talking about. You start off by building a masonry pier. When your masonry can't handle the load, you reinforce the pier with a cast iron column. And then when you want to have a frame, excuse me, that is independent of the masonry, you have to start supporting the wall on the frame. This is two excerpts from the 1892 New York City Building Code. It's funny because they're actually very clear when you read them, but I think the way that people react to them is not necessarily understood. This on the left shows a section through a wall that's over 100 feet tall. It's actually 150 feet tall as shown here. And what they're showing is that every 25 feet the wall has to get thicker. You can see the wall stepping out. This was a code requirement. This is example number 14. There were similar code requirements for different types of buildings. One thing that's interesting is that in 1892, the concept of a modern office building was still new enough that this is listed as warehouse walls, which are for buildings other than dwellings, except for churches, theaters, and schoolhouses. They didn't think to have a separate class for office buildings. This is prescriptive. This says that if you have a 150-foot tall building, and it is warehouse use, including offices, the wall will be 16 inches for the first 25 feet and get 4 inches thicker for each 25 feet in height, 25 feet being more or less 2 stories. Which meant that by the time you get down to the curb line, your wall is 36 inches thick, which is, not nothing. And when you have relatively small windows, as buildings in that era usually did, they sort of start to become tunnels through the masonry. The most extreme example of this that is still in existence is the Monadnock building in Chicago, where the walls at the base are 6 feet thick, and the windows are very much tunnels through the masonry. There's actually no arguing with this. This is based on the geometry of the building. This paragraph here describes that depending on the geometry of the building, how deep the building is, and how wide, how long the spans of the interior floor beams are between walls, you may need to make the walls thicker. But there's no escaping the logic of it. There's nothing to analyze here. It is an empirical design based on the building geometry. This assumes bearing wall construction, and it's a little difficult to see, but they actually show the beams bearing on the walls. This is several pages later in the code. It's a little misleading. It says curtain walls for skeleton structures, but this includes cage frame buildings. So this basically applies to any building where the masonry is not supporting the floor beams. So you have columns built into the wall, as I've been talking about. And it's 12 inches, and it gets 4 inches thicker every 50 feet, every 4 stories rather than every 2 stories. So by the time you get down to the curb line, it's only 24 inches thick. So you've saved a fair amount of the volume of brick by switching to this construction. It actually gets more extreme than that. First of all, Chicago distinguished between cage frame buildings and skeleton frame buildings. So by the late 1890s, Chicago was allowing you to build, excuse me, the continuous thickness wall top to bottom if you had a skeleton frame building. In 1892, when there were very few skeleton frame buildings already in existence, the New York Code did not distinguish between cage and skeleton frames, and didn't actually make that distinction until 1901. You could write to the building department if you were an architect or engineer or a builder and say, you know, my wall is not freestanding. I've supported my wall on the steel frame, and therefore I would like permission to not have to make it thicker like this. And in most cases, the building department would agree and give a variance on that. So when I started looking through records at the building department of early skeleton frame buildings, I kept finding these variations on this exact same letter from the architect or engineer who was working on the building saying, it's a skeleton frame building, the masonry is supported on the steel, we would like permission to not have the wall increase in thickness, and they typically always got it. So even though this is in the code and seems inescapable, the fact that it was sort of blurring the line between two types of new technology, the cage frame building and the skeleton frame building, led to a little ambiguity that people were able to not follow this. This was inescapable. If your beams were bearing on the wall, you had to do this. So I guess the thing about these two code sections that is most important from the technology standpoint is that there's no analysis. This is not engineering. This is an empirical design, excuse me, that couldn't really be rationally analyzed. Bragging a little bit here, this is what engineering analysis looked like before everybody had a calculator. One of the popular ways of doing analysis was graphic statics, and that's what this starts to look like. So the point of this is that steel framing, unlike the brick walls, required fairly complicated engineering analysis, and therefore couldn't be reduced to a few simple diagrams in the building code. The building code said that you had to follow, and they usually gave a source of allowable stresses, but you had to follow engineering rules, not the code for design. And this was the building code sort of recognition that there was a difference between the empirical design of masonry and the analytic design of the metal frame. So I wanted to look at what would happen if it were 1895 and I weren't an engineer. If it was 1895, how would I decide which of these three types of technology to use? So I came up with a sort of a generic model building that's fairly similar to a lot of buildings that were built in that era. The bearing wall version of the building has exterior walls and also has these two interior walls. So you have 3 spans of beam across the width of the building, and the walls get thicker as you come down the building as required by code. There was nothing for me to do there. I did come up with a size of floor beam that made sense for that era. I should mention that in these models, I'm only looking at the bare structure. I'm not looking at the cost of elevators, stairs, windows, plumbing, gas fixtures, or the newfangled electric system. I'm looking just at the structure of the building. Cage frame building, the walls still get thicker, but not as much. The 2 interior walls have gone away and have been replaced by cast iron columns. And I also have cast iron columns at the perimeter. And then in the skeleton frame building, the walls are constant 12 inches top to bottom. The whole thing is now steel, and I have the steel details required to make that work. So it's sort of a fairly straightforward simplified version of the three types of technology that were available in the 1890s and were all still being used in the 1890s. And this is where things get sort of interesting to me. So the amount of brick, in the bearing wall building we have 4,900 tons of brick. It's a lot of brick. I seem to remember it being something like 120,000 individual bricks. The cage frame building, we don't quite cut that in half, but pretty close. And then the skeleton frame building, it gets reduced again, but not as much of a reduction because the cage frame building already had gone to skinnier walls and had gotten rid of the two interior walls. There's only cast iron in the cage frame building. The weight of steel goes the opposite direction from the weight of brick. It goes from 180 tons of steel, all of it floor beams in the bearing wall building, to 250 tons in the cage frame building, and then it more than doubles in the skeleton frame building from adding all of those steel columns in. Using, a few minutes ago, I discussed 5 factors that affect the cost of things. So using the costs from 1895, how much does it cost to make brick, how much does it cost to ship brick, and so on. The cost of the brick walls in the bearing wall building is $111,000, more or less. The cost of the brick goes down in the cage frame building, goes down again in the skeleton frame building. The cost of steel does the opposite. It goes from $11,000 to $33,000. So if you look at the bare structural cost, again, this is not a usable building. This is a structure with, among other things, no way to get from one floor to the other because I don't have any stairs in here. But if you look at the cost of this structure, it goes from $120,000 more or less to $75,000 more or less, which implies that people were saving money if they used the new technology. Now, I'll come back to that in a second, why that would be true. This cost, so if you divide by the usable square feet in the building, the cost of the bearing wall building is a little over $2 per square foot, drops down to about $1.30 per square foot in the skeleton frame building. I should mention that the usable square feet is bigger in the cage frame building than the bearing wall building because the walls have gotten thinner, and the usable square feet in the skeleton frame building is slightly bigger than it is in the cage frame building. Again, the walls have gotten thinner. So the thing I'm dividing by here at the bottom, the square footage, is not constant. It gets bigger even though the overall size of the building hasn't changed. So why would this be true? And I think the way to understand it is to look at the total weight of structural material. You're over 5,000 tons of structural material in the bearing wall building. You're at around 2,300 tons, less than half weight of structural material in the skeleton frame building. What you've done is replace that huge mass of brick with much less metal, which makes sense because steel can take much more stress than brick can. Steel is a designed material and inherently stronger than brick. So when you add that together, what you're doing when you're switching from an empirical design, which means a lot of brick that's not very highly stressed, to an analytic design with much less steel, but it is much more highly stressed. It's doing more work for you. Why would it cost less? It costs less in part because you're getting rid of material. It also costs less because of the nature of the material you're getting rid of. Bricks themselves are prefabricated, but that big brick wall is not. It has to be laid up by skilled craftsmen on site. The steel is mostly shop fabricated. It's mostly done in a factory somewhere. You need skilled labor to assemble the frame on site, but it's much less. The fifth item, which was actually building the thing on site, you've gotten rid of most of the work by switching from brick to steel. So again, you're saving money there. So taking those factors into account, the fact that the cost gets less as you go to the newer technology isn't really a surprise. The biggest surprise for me was that you save most of the money in going from a bearing wall building to a cage frame building. And that's true because you've gotten rid of the two interior bearing walls, and the walls that are left have gotten a lot thinner. So you've gotten rid of most of the mass of brick by going to the cage frame building. You get rid of a little more by going to the skeleton frame building, but it's nowhere near as big a change. So if you look at this if you pretend you don't know how this whole story plays out, and you look at this solely from the viewpoint of what's the lowest first cost, it makes sense in 1890s to switch from a bearing wall building to a cage frame building, but it doesn't necessarily make sense to switch from a cage frame building to a skeleton frame building. So the fact that people didn't immediately jump to use skeleton frame technology is in part because there wasn't a cost push in that direction. There was some, but it was a little blurry. I should also point out that these costs per square foot on my models more or less are in agreement with the costs of buildings being built at the time. So if you look at buildings about this size being built in New York in 1895, they run from $1.90 maybe to about $4.50 per square foot. That's for the whole building, with windows and elevators and stairs. So the structural costs here seem about right, given those total building costs. A few years later, 1912, this is Detroit City Hall, but that's not the building I'm looking at. This is the headquarters of Dime Savings Bank. I should point out that this building on the left here is the Detroit Chamber of Commerce, and it is an early skeleton frame building from the 1890s. So some 20 years, 15 years, 20 years after what I was just talking about, here's the final product. This is the steel skeleton frame skyscraper as it existed in the early 20th century. It was the result of all of this change. And you can see a bunch of things. First of all, the construction of the framing is completely decoupled from the construction of the wall. The wall serves no structural function, so you can have 10 stories of bare frame, and it works just fine because the frame is where all of the structural capacity is. Beyond that, you can start and stop the wall as you need. You can have a missing section of wall in the middle, and it doesn't matter because, again, the wall is serving no structural function. So if you look at these two skeleton frame buildings, constructed not quite 20 years apart, the wall at the Dime Savings Bank is a thin wall. It's a 12-inch wall, top to bottom. The walls at the Chamber of Commerce are much thicker. If you looked at that building and didn't know it was a skeleton frame building, it would take some time to figure it out because the walls could be bearing load. They're big enough and they're strong enough to do so, but they weren't meant to. Whereas the walls at the Dime Savings Bank are clearly inadequate for the structural load of a building that size, therefore it has to be a skeleton frame building. And it's clear when you look at a modern building like this what the structure is. It's these early buildings, like the Chamber of Commerce, where it's not so clear, and you have to start looking at the little details to see how they were put together. If you look at the overall story that I'm talking about here, what's happening is that old-fashioned technology, that very first slide I had of the New York Times building being built, which relied on old-fashioned brick on top of brick, stone on top of stone, that kind of technology was being replaced by modern industrialized technology. There's a huge difference between making brick, even the modern industrialized version of making brick, and the creation of steel, fabrication of steel. It's a very different level of industrialized technology, and the introduction of that into buildings is an integral part of this change from bearing wall buildings to skeleton frame buildings. Without the industrial processes that get you modern steel framing, you don't get the skeleton frame building. And it's important to remember that those processes were not put into effect, were not invented to enable steel skeleton frame buildings. They were invented to enable steel bridges and expansion of railroads, which was going on long before steel skeleton technology was being used in buildings. So you've got this sort of existing technology, ironworkers and engineers who are comfortable with building braced frames out of steel, and it gets absorbed into the building process as skeleton frame technology.
Thank you, Don. I'm going to jump in here just to ask a kind of postscript question, and I want to mention to everybody that they really need to get Don's new book called Structure of Skyscrapers, where all of the arguments here are just a small portion of this incredible encyclopedic knowledge that he has, both of engineering and from an analytical perspective, but also as a historian. So I want to ask you this historical question about how you collected the information that we see here. It's very summary, and you have an example, but I know for a fact that Structure in Skyscrapers is at least 10 years worth of data collecting through reading the engineering journals, through going through old building records in cities around the country, not just in New York and Chicago. So can you talk a little bit about what lies underneath these numbers? I'll get out of the frame.
Sure. What lies behind this chart is about 30 pages worth of calculation. So going back to those 5 factors that affect cost, if we look at this number here for the weight of steel and the cost of steel in a skeleton frame building, I had the amount of steel from my model. That was just me being an engineer designing a building in very rough terms. Various journals give me the different prices for the different pieces of it. So for example, there's a journal called The Iron Age, which covered everything involving steel, from structural steel for buildings down to the cost of cutlery. It was just an amazing journal. And if it involved steel, it was in there. And that got me the cost of raw steel, it got me the cost of fabrication. Various engineering journals, largely the Engineering News and the Engineering Record, got me the cost of shipping, which is that. Got me the cost of fabrication came from the Iron Age. The cost of hauling, I don't remember now, it was, I think that was from the Real Estate Record and Guide, which was a New York real estate journal. So different journals had different pieces of this, and I had to convert. Some of them were based on tonnage, some of them were based on per piece. So I had to do the conversion to get everything to the right units. So this 520 tons of steel represents so many pieces, each of which is a certain size and a certain weight. And by using those factors, I was able to convert that to a given price. And it was the same kind of calculation. There were journals for masonry, there were journals for cast iron, and taking the unit costs, getting the right units. So cast iron tended to be per piece because a complicated piece cost more than a simple piece. So I had to make a judgment call about how complicated were the columns I was looking for. And since they were interior columns and wouldn't have needed any ornamentation, I said they were sort of medium complicated. They were columns, and therefore they had to be made properly, but they didn't have all of the frou-frou that you see on a cast iron facade. So sort of pulling together the different pieces for brick, the cost of building a brick wall was pretty well documented. But then these are 12-story buildings that I was looking at, and the cost goes up as the building gets taller because they have to build more and more scaffold. These days, we wouldn't build a scaffold from grade all the way up to build a building, but that is what they were doing in that era, so I had to sort of throw that in. So it was a lot of what is done today when you have a project and you send it to a cost estimator. It was that kind of calculation. Just based on 1895 prices rather than current prices. And in some cases where I couldn't get an 1895 price, the Census Bureau has tables to convert prices from different years. So I was able to take an 1898 price and convert it to an 1895 price.